Look at the sheer speed of modern automation. Executing a complex physical maneuver seamlessly requires absolute mechanical precision. But designing lines that can sustain this performance requires orchestrating physical hardware and digital control networks simultaneously. Mechanical engineering alone cannot achieve this. The operational tension lies in the physical constraints. We are routinely chasing micrometer-level geometric tolerances on fabricated parts at high speed. To maintain that level of exactness across a highly variable product mix, the physical layout of the factory floor must be tightly coupled with a hierarchical IT and OT control network. We are going to construct a modern automated line from the ground up to observe how physical layout and digital integration must be co-designed from day one. Treating software integration as an afterthought to hardware selection is the primary root cause of integration failure, and it directly degrades cycle times. The design begins at the discrete workstation. Initial machine selection is governed strictly by cycle time targets and operator ergonomics. For parts with complex geometries, manufacturers often deploy hybrid setups that combine additive manufacturing directly with traditional CNC machining. This diagram compares cycle time architectures. Left, a single hybrid node processes a shape, reducing geometric deviation since the part never leaves the fixture. Right, it moves across 3 slower nodes. The trade-off? The single cell requires hyper-precise fixturing and thermal control. These specific hardware choices immediately dictate the process planning constraints for the rest of the facility. Physical workstation architecture sets the ceiling for overall system throughput and establishes the hard limits for all subsequent software flexibility. Once individual workstations are defined, we have to map how they physically connect. In spatially constrained environments, rotary tables compactly sequence operations and pass materials between stations. For larger footprints, that layout expands to rely on continuous conveyors and transfer robots. The spatial layout determines the buffering strategy, which shapes how materials flow through the automated line. The primary logistical failure point in these setups is transfer delay, often caused by cranes or automated transfer devices. A single bottleneck in material handling cascades rapidly, creating substantial idle time across workstations that are otherwise fully functional. This top-down flow network demonstrates evaluating system stability versus flexibility via simulation. Running these studies lets architects quantify how expansion impacts cycle times. Data-driven analysis then dictates exact physical buffer sizing, preventing over-provisioning while maintaining flow. We then introduced IoT-enabled real-time state awareness into the material flow network. Automated systems use this live IoT data to calculate optimal equipment allocation, drastically reducing uncertainty in transfer device scheduling. Optimal material flow is a data problem. Physical conveyors only eliminate idle time when governed by algorithms that predict and standardize transfer delays. The interface where physical hardware translates its actions into digital data is the edge sensor network. This synchronized graph compares electrical signals with physical reality. The top tracks a spindle drive's current waveform. The bottom plots physical degradation of a tool flank over the same time axis. Mapping these currents provides a highly correlated, non-invasive signal for predictive maintenance. When executing physical movements, mapping these sensor inputs to actuator commands, like servos or pneumatics, must respect absolute real-time safety constraints. Success here is dictated entirely by network protocol implementation, utilizing industry standards like Modbus TCP over IP. Properly configured industrial protocols must achieve sub-0.01 second transfer times across the workshop to support real-time operational decision-making. High-fidelity sensors and advanced robotics are useless if the underlying network protocol cannot transmit edge data fast enough to execute a corrective physical action. Moving up from the edge sensors, we construct the hierarchical control model that governs the entire line. This chart illustrates the control structure. Base-level PLCs execute machine sequences via rapid horizontal data loops. Upward streams feed SCADA, MES, and PLM layers. The conflict is ensuring low-latency data for fast PLC loops, while simultaneously feeding latency-tolerant analytics above. The practical barriers to deploying this structure are substantial. Protocol mismatches between these layers drive up both procurement and training costs. The architectural solution is implementing dual redundant field bus structures, like Profibus DP, to protect critical execution paths and improve system robustness. Failing to architect a rigid boundary between deterministic machine controls and latency-tolerant analytics guarantees system-wide errors caused by stale-state data. We can connect the highest level of the software hierarchy, the PLM, back down to the physical floor through a digital twin environment. PLM systems extract module-level data and facility information to populate highly accurate production simulators. This split interface shows virtual debugging. New configurations are scenario-tested online before physical commissioning. For this to work, architects must execute exact real-time mapping of module outputs to MES inputs. Digital twins only shorten commissioning cycles when their virtual data flows perfectly mirror the exact constraints of the physical factory floor. Look at the scale of a fully automated facility functioning perfectly in real time, without any visible human intervention. The ultimate throughput and precision of an automated line are bound by integration quality, not isolated machine specifications. Avoiding latency mismatch across the facility requires staged integration, explicit data mapping, and comprehensive training plans across both IT and OT departments. To achieve next-generation manufacturing capabilities, the modern industrial architect must design the digital control network and the physical factory floor as one unified, indivisible machine.